Okay, very good morning to everyone. The topic that we're going to discuss for today is intelligent speed control of DC motor using fuzzy algorithm. So my groupmate consists of Lim Wei Kong, Yong Wei Chong, Leong Ming Rui, JEYARAJ, and myself, VAIRRAVEL Kumar. Okay, next slide. Okay, for the introduction, direct current motors, which are known as DC motors, are widely used in a range of applications that demand for high-speed control accuracy and dependable, effective dynamic response. So DC motor speed is also related to the armature voltage and inversely proportional to the magnetic flux generated by the poles. As you know, PID controls are the most well-known controls in the market because they have the ability to calculate the difference between the desired temperature set point and the current process temperature and then predict how much power need to be used. A fuzzy logic control is also an intelligent turning method that employs a language control algorithm based on general statement rather than mathematical calculation. For the control of series of DC motor and improved evolutionary method to regulate fuzzy control setting has been described, there are many research also gives an appropriate approaches to determine the optimum control. Okay, next slide. For the problem statement, PID controllers are hybrid intelligence are commonly used to control a scheme because of their simple structure and their comprehensible control algorithms. The performance of a PID control is also determined by the precision of system models and their parameter. PID controls are frequently insufficient in systems with unknown complexities such as time delays, oscillatory behavior, non-linearities, and the MIMO system, which is multiple input and multiple output system. Next, the expense of control operation attracted attention of industrial sector where creating a computer-based control could have saved money and effort because it's portable. That's all from me.
Okay, thank you, Vera. Next, I'm going to explain on the PID and IPD and FLC controller, where a conventional PID control is made up of parallel, structure, integral, and derivative actions. Its construction describes the definition of three parameters, which are P stand for proportional, I stand for integral, and D stand for derivative. So the second controller, which is the IPD control, is obtained by rearranging the PID, which is the only difference is the integral will action as the output, while the proportional plus derivative will act as the output. So the third control is the physiologic control, which is made up of a control structure with rules and gains, as well as the fuzzy reasoning process. So fuzzy logic control is a method to non-linear controller design that readily incorporates with human knowledge and critical aspects. So physiologic control does not require a precise mathematical model where it can cope with various inputs, can tolerate non-linearly, and has a higher disturbance sensitivity than non-linear controllers. So next, I pass to Lim Wei Keong.
Thank you, Jeyaraj. So I explain the block diagram. As you can see here, we have about 7 structure. As first of all is the input system. We have the voltage supply V, we have the PID controller as the first controller, and we have the actuator, which is armature. The actuator is a function to convert the control signal to the mechanical motion, and we have the rotor, which is provide the rotational speed. As output system, we have the W, which is in radian per second. And lastly, we have the speed sensor Arduino function to give the feedback signal to the initial of the system. And lastly, we use intelligent controller, which is fuzzy logic controller, in order to help our system to achieve an optimum condition. Next. For the transfer function part, as you can see here, the transfer function for PID controller involves 3 mathematical model, which is first is proportional, second is integrator, and lastly is derivator. And transfer functions for actuator armature is about 1 over Lx plus R. For transfer function for plant rotor is 1 over Jx plus V. And transfer function for sensor is the Kb multiplied with the delta of the derivative of delta, okay, to get the speed sensor for the Arduino. So this is the block diagram for the DC motor. That's all about me. I will pass to Leong.
Okay, thank you, Lim. So I'll share about the simulation of fuzzy PID FPID in DC motor using Simulink. So first, the subsystem of the DC motor is created based on the transfer function provided in the journal with the motor parameters as in the first table. Then PID controller is created from scratch to create initial value of PID as in journal. So the value are listed in the second table, where the PI is the initial proportional gain, II is the initial integral gain, and DI is the initial derivative gain. Next. Okay, so afterwards, fuzzy logic design is used to create the fuzzy logic controller, which is a 2-input, 3-output FPID controller. So in the journal, triangular membership function are used for fuzzification, in which the second column of table are the input and output. So the input are error E and change in error CE. The output are dynamic proportional dp, dynamic integral di, and dynamic derivative dd. Then the third column of table shows the domain of input. The second column of table shows the domain of input and output, in which the input space are in the third column. So the input space for error is low, medium, and high error. Input space for change in error is low, medium, high change, and output space for dp, di, dd are low, medium, high gain. And then finally, we have the bottom half, the membership function plots, in which those with yellow background is input, blue background are output. Next. Okay, so these are the rule base for FPID controller. So for example, if the error is low and the change in error is low, then the DP, DI, DD will have low gain. So the rest are similar. Other than that, we also use fuzzy Mamdani fuzzy inference system and centroid method for declassification. Finally, all the subsystem and fuzzy logic controller are combined into FPID controller for DC motor. So the performance of controller can be observed and analyzed using the scope. So that's about it for my part. I'd like to pass to the next speaker, YEONG. Thank you.
All right, for result, firstly, we have the result of control set from the journal. So it is observed that the speed of the motor achieves a steady state quite fast at the steady state value of 1 radian per second without unnoticeable fluctuation at the graph. And then all the graphs have no peak-to-peak amplitude due to the short rise and settling time. Besides, all the graphs are said to be stable as the speed achieved at the steady state in all graphs. So firstly, it is the domain of dp changes. When the domain of dp decreases to the 0 and 3.6, you can see that the percent overshoot is increases significantly, and the rise time is increases and the setting time is increases. This is because when the dp decreases, the reduction of the rising time and steady state error decreases. So now for the domain of dp at 0 and 10.8, it has a negative percent overshoot of negative 0.179 because this is because it could not achieve a steady state at 1 radian per second after 3 seconds, where the negative percent overshoot means that it will never go above 1 radian per second. And the rise time is very reduced due to the increased effect of the proportional gain. And the high dp, that means that it will reach a steady state value of less than 1, so it will take a longer time to push it to 1 radian per second. Next. For changing of the domain of di, so we can see that as the di increases, the percent overshoot also increases, the rise time decreases, and the setting time decreases. This is due to the properties of the integral gain, which will maintain the minimum steady state error, but will significantly increase the overshoot of the system. So lastly, we have the changing of the domain of dd. As we can see here, the percent overshoot increases as dd increases, and the rise time increases a little bit while the setting time decreases. So the function of dd will significantly decrease the setting time as following the trend. However, according to the rule base, the output of derivative gain should be inverted as compared to the output of the proportional gain and the integral gain. So at the low error and change in error, the higher derivative gain should be applied. However, in the journal, the rule base is a little bit wrong, where the derivative gain is too small to suppress the overshoot. So the percent overshoot will be increased as the dd increase. So next, I will pass it to the conclusion.
Thank you, Yong. So in conclusion, the fuzzy PID FPID controller for DC motors created and simulated in Simulink using MATLAB software. Fuzzification has been studied by using triangular membership functions. So we also can conclude that when steady state value at 1 radian per second, by changing the domain dp, when the percent overshoot increases, the rise time and settling time also increases. By changing the domain of di, as the percent overshoot increases, the rise time and settling time decreases. While by changing the domain of dd, when the percent overshoot increases, the rise time increases, but the settling time decreases. So we also can conclude that fuzzy PID controller can be a better alternative for process control than the normal PIDs. So that's all from us. Thank you.